Okay, it's 9:45. Let's get started. Good morning. So last day, right? So we are going to wrap up things. What I want to do today is we're going to revisit a little bit about the anisotropy, because when I covered the vertical versus horizontal modulus, because there are so much things, I kind of rushed it. So I wanted to go back a little bit and explain to you what anisotropy is. Then what I wanted to do is, if you look at the original program, today was a lot more about railroads and stuff. And what I decided is to merge railroads in general with some other transportation geotechnics research. So now we've covered essentially the most important fundamentals, right? So now I want to show you some challenges that are there and some of the work that we have been doing in my group and stuff. So we'll go over some research overview essentially, and we will also do a demo of this software called GeoTrack. That it's a story. It was developed long back, but then the source code was kind of lost. So back in 2015, we kind of redeveloped it in my group. Based on the same principle, exactly same principle, but we kind of rewrote the coding and we developed a MATLAB based GUI. I'm going to demo that for you. I cannot share it because it is actually somebody else's intellectual property. So I'm actually not allowed to share it. I'm allowed to use it in my group, but I cannot share it with you all. At the very end, I have a Menti link on some course feedback and stuff. I know that the official feedback that's going to happen based on the paper, but I do some stuff on myself. So we'll do that. We'll kind of wrap up and everything. And on the tutorial today, we're going to do this thing has been pushed from day to day because of other things and stuff. So we will talk some of that today. Okay. So before so the very first thing is we're going to talk about anisotropy and stress path testing. Okay, and I want to illustrate what the stress path was. I skipped over this very quickly, and I just want to highlight what it is, the underlying principles. So let's revisit what we were talking about. If you are talking about an aggregate layer, and this anisotropy is in regards to aggregates primarily, what happens is when you have aggregates and when you compact the aggregates, a kind of a preferential orientation, if you think about it, they kind of each other. And when you do that, then the load that gets applied, because it actually dissipates at certain angles and stuff. And as we know, Hooke's law and stuff, we have epsilon 2 directions and epsilon 3 directions and everything. If you do Cartesian coordinates, x, y, and z stuff. So what will happen is that your modulus in a generic formulation, you assume that it is the same in all three directions, and your Poisson's ratio also gets assumed to be in this same in all three directions, and that's the property that we call is isotropic, right? But what I introduced is that because aggregates orient like that, and then still if we look at a certain plane, it is still axisymmetric around the horizontal plane basically. So it's similar on the horizontal plane, but if you compare vertical and horizontal, it's going to be different. And that is the reason we use the word called cross anisotropy. If you had a way of taking your triaxial specimen and then applying loads in multiple different directions, then you would see that the MR in H is not equal to MR. Okay, now this H, I am talking about is the horizontal, where I am still merging the 2 and 3 directions. I am not separating. Now, if you have a true triaxial setup, right, if you had a true triaxial setup where you actually had the ability to control all the walls, you would be able to test whether 2 and 3 are also different or not. But we're not talking about that right now. We're still talking cylindrical triaxial, right? So MRH is not equal to MRV, and that is what the concept of the fast cell was, which is where, and you did this already in the data analysis. What you did is you had a sigma h comma static, and then you had another ability to do sigma h comma deviator, and then you do sigma v comma static, and then you do sigma v comma deviator, right? So when you pulse in the horizontal direction, and then you actually are able to measure or track the modulus values, then you actually see that MRH is actually pretty small compared to MRV, and if you look at the comparisons, the factor is close to about 0.3, about 1/3. Okay, so what does that mean? What is the significance of this? The significance of this is that when you are doing an isotropic analysis, and if you are assigning the same modulus in all directions, then it is you're equating everything to vertical modulus, right? So you're saying that MRH is also the same as MRV, then what will happen is that you are overestimating the stiffness of the layer in the horizontal direction. And if you're overestimating the stiffness, then sigma over E is your strain. You are underestimating the strains, right? If you're underestimating the strains, you are underestimating the pavement responses, right? And you are you're underestimating response, so you are now overestimating pavement life, because your prediction functions are based on that, right? So that is the reason, that is the whole reason this setup was designed. And what you can do is actually pulse in the horizontal direction, and we had some equations. It's not in this one. I can pull it up quickly for you. This is the setup, this is the thing, and now you are talking about when you are pulsing, horizontal pulsing, when sigma 1 d is equal to 0, or sigma vertical d is equal to 0, then your epsilon 1 you can determine, and epsilon 3 you can determine, and MRH, because you are determining, look here, when horizontal pulsing you are determining MRH, in the vertical pulsing you are determining MRV. Right? So now you are able to isolate and separately determine the two resilient modulus values. Is this a very common test method? Absolutely not. I mean, there is probably, maximum, if you take the entire world, maybe 4 or 5 test equipment that can take care of something like that. But that's basically where the science should be going in terms of characterization, in terms of anisotropy and stuff. And the GT-PAVE, that was written by Professor Errol Tutumler when he was a PhD student, that actually has the ability. Well, you played with IIT already, right? So GT-PAVE, which again I don't have the current version, I can't share. The point is, there, instead of just assigning k and n values in the vertical direction, you also have the ability to assign k and n in the horizontal direction as well. So it does independent calculation of MR in the horizontal and vertical directions. Okay, so this is what I showed you about the Uzan and stuff, how you fitted it, and this is what I was trying to say is MRH. There was a paper where what they were able to do is they were able to use this modular ratio as or modulus ratio as an indicator of material quality. They were able to say that, okay, for a good material, they should be close to each other. For a bad material, it should be very, very different because it's not aligning and stuff. That's what this Fred Berggraf award is and stuff. Okay. We talked about some of these. I want to also focus a little bit on, not this one, where is the other one? This one. I want to focus a little bit about stress path testing. Okay. So stress path in this context, we are defining P is the mean stress, so divided by 3, and Q is basically the deviator stress. If you look at the definition, so P is basically theta over 3, and Q is equal to sigma 1d minus sigma 3d. Okay. Why is this important? What is stress path? I mean, those of you who have taken, advanced geotech classes and stuff, you know that stress paths are basically, it's almost like a history. It's like a health history of the soil. You can see how is it being loaded, what is the stress it is experiencing, and it can plot it on a PQ plot basically. So if you look at it, the x-axis is P and the y-axis is Q. Let us take our traditional resilient modulus test. Traditional resilient modulus. Okay. So if you remember, I'm going to just work on the first pulse group or first sequence. So sequence number 1, your sigma 3 is what? Who remembers? 3 psi. Sigma d is 3 psi. Sigma and then so sigma 1 basically becomes 6, right? And then let's do number 2. 3, 6, 9. 3 is 3, 9, 12, right? What I want to do, the exercise here, is let us calculate the P and Q values for each of these stress states. Okay. So let's go through this. So what I said is P is theta over 3. So let's do theta here. Theta is what? Sigma d plus 3 sigma 3, right? That's what it is. So sigma d is 3 plus 9 is 12. Yes. Now I'm going to make another column for P here. So I said P is theta over 3. So it's 4. Let's do this one. Sigma d is 6 plus 9, 15, 9 plus 9, 18. 6. Yes? Are we cool on this one? Okay. Now Q. We said sigma 1d minus sigma 3 d. Sigma 3d in the vertical pulsing is how much? 0. So Q is basically this, right? 3, 6, 9. Correct? Now let's do a PQ plot. P, Q. The first plot is 4, 3. 4, 3. Second plot is 5, 6. So 5 somewhere here, 6, here. Right? Let's find the slope for this line. What is it? 6 minus 3 divided by, what is it? 3. Correct? Now let's go to the next stress state. What is this? P, Q is 6, 9. So it's 6, 9 somewhere here. Okay? So what is the slope between here and here? 9 minus 6 divided by 6 minus 5 is 3. So your traditional triaxial or resilient modulus testing on a PQ plot, your test slope is 3:1. Okay? That is how what you are subjecting it when it is vertically on top of you and you are actually just pulsing. In the advanced triaxial testing, what we are saying is that it is not always vertically on top of you. So you should not be pulsing just vertically. So your stress path slope should not be 3 all the time. Okay. So that is the whole concept of this variable confining pressure and stuff, and you can actually go somewhere. Here you can have static failure is over here, so you can change 3:1 all the way to, if you do horizontal pulsing only, okay, then it becomes like a minus 1.5 kind of a slope. Okay. So what is horizontal? Horizontal pulsing is the extreme case, right? This is one case. This is completely another case when the stress path has completely rotated. But as you know, in these plots over here, here you see that it gradually rotates, right? If you do that, it basically gradually rotates as the soil moves. So the whole idea about this one is that you are trying to find ratios or proportions of different vertical and horizontal pulsing, and you can come up with another pulse or slope completely. Does that make sense? So there is actually one sequence where you can actually do both of them together. Okay, so let's find that out. Let's try to do. So that's one extreme. So, oh crap. Okay, I think what you can do is, I'm going to do this, and we are going to do sigma 1d here, and we're going to call this is sigma 1d. I'm going to write sigma 3d, and then I'm going to calculate theta, and I'm going to write p, and I'm going to write q. Okay, and this is basically the exact same. Imagine Astro T307, but now you are doing both pulsing together. You're not just pulsing this way. So what is the confining? Still 3, right? 3, 3, 3, right? The pulse is 3, 6, 9, and we're pulsing both now. So now let's try to do a theta. Help me out. I don't know any numbers, so I may make mistakes. So sigma 1 comes out to be what? 6, right? Sigma 2, because you are pulsing the entire thing. So sigma 2 and sigma 3 are still the same, right? So sigma 2 and sigma 3 are both 6 as well, right? Isn't it? Yes. So what is theta? 18. So P becomes 6. Q is sigma 1d minus sigma 3d, which is, right? Now let's do this case. What in this case, what is sigma 1? 9, and they are also 9. So 27, right? And then P is 9, and what is this? 0. So trace this. 6, 0, 9, 0. So now it's moving along this line, along the P. Okay, so it's one case of stress path testing and stuff. Now when you try to do a model, complete model, and you actually say that, okay, this is where my wheels are, this is where my wheels are, and this is the stress path what it is. Let's just say you are trying to study a repeated load, like the NAPTF, the National Airport Testing Facility. They have a huge system where they actually mount aircraft gears and they load. right? So you actually install pressure sensors and stuff, and you measure that, okay, this is what I am seeing for my aggregate in terms of sensors. So now you calculate P and Q really, and then you actually go to this advanced triaxial and you actually program it so that it actually does the exact same repetition. Then you can have a better simulation of what is happening in the field. Does that make sense? So that is what this whole stress path related thing is. You have independent control and you can do whatever you want to. You basically you're simulating. You are not always saying that I am on top, I'm only pole plotting, I'm only pushing vertically. That's essentially the whole story. Okay? All right. So that's one I wanted to cover. Now let's go a little bit into on the last day today. Let's go a little bit into railroad tracks. Okay, so what I have is we will go into railroad tracks through some research presentations and stuff, and I will spend some time to explain to you all what's going on and how that happens and stuff. Okay, so this is kind of our it was kind of some work in my group with some focus on railroads, some focus on transportation geotechnics primary. So we'll go through that. There is some overview of pictures of my group, some work that we do. I'm going to skip all of this. We do a lot of finite element modeling, dynamic stress propagation. Okay, maybe you should see some of this. So I have been talking about lightweight deflectometer. So this is some instrumentation stuff. This is lightweight deflectometer. If you see that, that's what this is. It's a single sensor in there. There is a load cell, and you can actually drop it, and you can actually measure deflection. That actually gives you a good buzziness. That's me testing on some railroad tracks. This is the same as the PhD work for the DCP and stuff. Do quite a lot of asphalt testing. We'll skip those, and we'll get into a lot of this today. The railroad instrumentation, I'll show you what this is and what not. And then we try to model all the phenomenon. Again, ideal research should always be a combination of theory and practical. So just experimentation will give you what. You need to see the why as well. That's the whole idea, right? So this is some railroad work under repeated loading. This is similar to what your deflection basin is. You can actually, so deflection basins happen in pavements and railroads. It's the same thing. Load is there, you have a display basin. You can actually generate large number of models, and then you can use something like artificial neural network, or these days some other form of machine learning and stuff, to actually calculate damage intensity and stuff like that. This is another stuff that we didn't cover at all in this class, is discrete element modeling. That's another thing I do quite a bit in my group. The difference is, how many of you have heard of discrete element modeling? Okay, heard of it. So it's not continuum. Like finite element is very good, it's a grid and stuff, but it still assumes that you are analyzing a continuum. If you go to an aggregate layer, it is not a continuum, it's individual particles. They have no cohesion there. It's not a continuous system, right? So you have to do individual particles, and you have to analyze or study the difference or interaction between them. Concept-wise, discrete element modeling is actually very simple. I mean, underlying concept, it is based on Newton's second law. You try to track rate of change of momentum, and then force, unbalanced force is rate of change of momentum, and then you see how the particles move, how they interact and stuff. But the actual coding and formulation of it becomes extremely difficult. So this is some ballast testing and some single particle breaking and stuff like that. And then you can model, you can calibrate the DEM with LWD. So this is some of our work with LWD being calibrated as DEM and stuff. Compaction, I showed you some of that. That's actually me driving the steel drum roller. That's actually one of my research projects. and this is another one very recent, which is where we did plate compactors. So this is unsurfaced pavements and stuff, open graded aggregate layer. So that's one area we have been studying for the last 3-4 years. This is last year. This is 2023. This is 2021, I think. So compaction studies and stuff. This is an overview as a drone footage. This is what happened in 2023 October basically. This is my students. We're constructing all these layers, and we had all these, plate compactors to compact and study how compaction works. And we'll go a little bit into those findings and stuff. Just wanted to show some stuff. Okay, so now let's talk about what I want to focus on, and a lot of railroad here and some pavements and stuff. We're talking about a combination. We have talked a little bit about lab characterization. We've talked a little bit about numerical modeling in this class, like with IIPave and stuff like that. But we haven't talked about field instrumentation at all, right? So that's what I wanted to focus on today, so that you have the cycle complete, right? So lab is a very simplified, assumed kind of a scenario. Numerical modeling is theory. There is a lot of assumptions and stuff. Field instrumentation is something that happens in the field. You have to bring all of that together. We need to monitor what we have. Then we need to verify hypothesis and evaluate alternatives, and then we study like the underlying mechanisms and stuff. So it's a cycle. So an ideal research should actually have all three of them, right? So that's what we're trying to do. So this is some lab testing stuff in my group. This is some field testing again, LWDs. There are different types, DCP, nuclear density gauge. These are all my students. Some past students, some current students and stuff. This is during COVID time. You'll see us with masks and stuff. This is 2021, and construction, all of this and stuff. This is LWD again. Geocells, I don't know if anybody is familiar. Some of you may be familiar. It's almost like a three-dimensional geogrid kind of thing. It relies on hoop stresses to study. So this is actually some geocell work happening in the group, and then I'm going to go to field instrumentation. So this is where the instrumentation part starts. Okay, so yesterday I showed a little bit about the problem of the bump at the end of the bridge, the railroad stuff and stuff. So we'll go a lot deeper into this. So this is a cartoon by a company called Geotechnics that actually said, every time you approach a bridge, there is a big bump, right? There is always settlement, and there is some way you need to fix this and stuff. And there is a lot. It's a lot very expensive, and the same happens in railroads as well. Okay. So as I said, it's steel on steel, and the other problem is when you are driving on a road, you can deviate from your lane a little bit. That's not a problem. On a train, you don't deviate from a lane. If you deviate, then you're done, right? That's a crash. That's derailment, right? So that's basically what led to this problem. And then I showed you a little bit this picture. So this is some problematic sites, and this is what is known as a space curve. A space curve, you can think of it, it's not exactly, but you can think of it that you're lying the rail in the space. You're just visualizing it in space in terms of coordinates and stuff. And if you see, there's a big dip here at the bridge approach and stuff like that. There's a big level difference. So how do you address that, and how does that how does that manifest? What is the primary reason? So the way we studied that is something called MDD, or multi-depth deflectometers, and this is a pretty fancy, pretty innovative way. Actually, South Africa is where it was developed at the very beginning for pavements, and then railroads, only about 2 to 3 projects in the entire world have used it, or some in South Africa. Outside South Africa, there is only 2 projects. In America, one was back in early 90s, and the second one was our project. So if you look here, it's actually pretty ingenious innovation. The way it works is you drill a hole, and the hole is only 1 3/4 inch in diameter. What is that? So 3/4 inch is 19 millimeters, and 1 inch is 25, so 29, 25, about 44 millimeter in diameter. Okay, and then you are trying to insert these sensors, and the sensors work in a very interesting way. If you see these screws on top, there is a tool you can actually mount, put it the sensor in, and you rotate the screw. When you rotate the screw, there is actually a rubber washer with some little balls that are built into it that is actually in there, and when the screw tightens, the rubber washer compresses, and in return it expands in the radial direction. When it expands, it grabs on to the side of the hole, and that's what mounting of the sensor is. Okay, so it's a very, very complex design, and we had to make all the sensors from scratch, and then we did this. This was the instrumentation stuff. This is all the parts, by the way. These were all individual, Autodesk models that were built in the lab, and then our machine shop built the entire sensor from scratch. And there was a research engineer in Amtrak. There is the railroad company. His name is Mike Thomas. He's from South Africa originally. He was the only one in the country, America, who knew how to do this, and he taught us, and we were able to do this and stuff. And you're installing this and stuff. And this is sample data collected. This is one train. As you can see, this is a freight train or goods train, as you call. So it goes over 180 seconds, almost like 3 minutes to pass. It's very, 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 very long and quite slow. 49 loaded cars, 39 empty cars. Length of the train was about 5,600. So 5,200 is 1 mile. So it's more than a mile. It's quite long. Okay, and then just like I explained yesterday, every LVDT gives you the deflection of that particular layer. So LVDT 1 is the ballast, 2 is the underlying sub ballast or whatever, foul ballast, then 3, 4, 5. So when you are drilling, when we drilled in the field, this is where we established the bore log. So this is the bore log we established by drilling. When we encounter different material, we make a note, we take measurements and stuff. So it's a live bore log, and then you go back to the hotel, and then you say, okay, my layer 1 was this many inches, so the first LVDT will be here, second LVDT will be here, and stuff. You decide, and then next day you come to the field, and then you install it. Okay, so then I showed you this yesterday. I'm not going to do that again. You know what I said is there is a lot of permanent deformation, and then they fixed it, another permanent deformation. This is transient. Okay, this is transient, and the y-axis is percent of total transient deformation contributed by individual LVDTs. So imagine there is delta 1, delta 2, delta 3, delta 4, all the layers, and you add them. That's the total delta, and this is transient under moving traffic, right? And then you are saying, out of that, how much is one LVDT contributing, which is the railroad ballast, the top layer. You can see it can go as high as 90%, 95%. So what that means is all the transient deformation you are seeing in your railroad track, a lot of it, mostly at the bridge approach, is coming from the ballast. So you have to somehow fix the ballast. Why not the subgrade? Because these tracks have been in operation for hundreds of years. Like 100, 150 years is not uncommon at all. And when you have loading for so long and stuff, pretty much all the subgrade has kind of been compacted pretty well. Stuff. Unless you have really bad moisture changes or something, you would not have that. So that's basically one of the findings, is that okay, the ballast, so bump at so the project was about how to study or how to identify where is this bump coming from. If you only measure the bump, if you only measure rutting, folks, right, in a pavement, rutting is the surface manifestation. Is that from the asphalt? Is that from the base? Is that from the subbase? Is that from the subgrade? How do you know that? Right? So there have been applications of MPDs in pavements as well. you know, it all started in South Africa, but Texas A&M have actually done quite a lot of MDD's work and everything, and the California Research Center as well. So then we said, this is there is a remedial measure. This is again pure railroad introduction to you, right? It's called stone blowing. Okay, what is stone blowing? If you look at the track, this is the rail, and these are cross ties or sleepers, whatever you want to call it. And then you have ballast. Actually, the ballast goes in here as well. It's called crib ballast. But of course, the load, it doesn't play a role in vertical load transmission unless you assume shear or something. Vertical load is mostly through this and stuff, right? When rail, when loading happens and stuff, a lot of times what would happen is the ballast from underneath a tie will somehow get displaced. So this tie would kind of be hanging like that. So the ballast effectively will be here, but this tie of hanging. Why does it hang? Why does it not go down with the ballast? Say it again. It's connected to the rail, right? It's hanging from the rail. It's not just sitting on the ballast. It's clipped to the rail. So the clip is going to hold it up. And the rail has a pretty strong bending stiffness. It's pretty strong, right? So one of the approaches to avoid this excessive deformation at this thing and the increased dynamic loading when the train is going up to it, going through this, is to lift this track and insert additional material that are actually almost like pea gravel, like very, very fine, uniform sized gravel or rocks and stuff, to create like a support layer underneath. Why this kind of layer? Because the mechanism is by blowing, you actually do it through an air compressor. You actually blow the material in because you don't have access to it. You have a little pipe and you're actually with air pressure, you're blowing the material. So the more uniform it is and stuff, it will blow easier. So that's basically, we propose this as a solution. So then this is us working in a railroad track. So this is how the stone blowing happens. You have kind of a funnel, and then you're pouring aggregate into it, and there is an air compressor. That's what this air compressor is, and then it actually blows into underneath the ties and stuff. So that's basically what this is us trying out the method before we go to the field, and then we went to the field and did that. And look what happened. Transient deformation at that track was all like this, and then you support it by stone blowing, you suddenly reduce the transient deformation significantly. That's because it is now better supported, right? What's the take home point is that you have a problem, which is the bump, right? You said, where is the bump coming from? And then you did instrumentation, you found that it is from the ballast and stuff. Then you're like, okay, I need to fix something in the ballast layer. One of the approach is the stone blowing, and then you do that, right? Forensic investigation kind of thing, and then you fix it. And look at this. Look at the vertical accelerations. So this is all through LVDT. So if you take the LVDT, you integrate, differentiate once velocity, differentiate twice acceleration, or you can do this through accelerometer as well. Look at the accelerations in June, then January 2015. Look at how small the accelerations become. Okay, and then May again it's starting to get bad again because it's repeatedly happening. Similar stuff is happening. So then we were like, okay, that's displacement. That's one thing that's related to LVDTs. How about loads? How does load work when you apply, when you have a train running on a track? How can you measure wheel loads? Okay, You can't just have a scale on there or anything, right? You have to have, and as the time changes profile, the wheel load also changing because it's steel on steel. So it's going to be a strong interaction. So a typical track, this is how what works. The green line. If you have a typical track, if you have a wheel standing on one tie, it takes something about 45 to 55% or 50% of the load, and then the next ties take about 20%, next ties take about 7-8%, and then it basically dissipates. That's how it is. And why does it happen? This is because of the bending stiffness of the rail. It dissipates between other ties and stuff. Right? Now, what is this? This is a form of deflection basin, if you think about it. Where is the load being applied and stuff like that, right? But if you have a, this is by the way, this particular plot is finite element modeling work. Let's just say I am artificially reducing the ballast modulus here from 230 megapascal to 2 megapascals. So it's almost non-existent. It's simulating this hanging tie condition. There is no ballast remaining. Why did I not do a complete gap? Those of you who have worked in finite element modeling, you will know if you create a gap and if there is deformation happening and two areas with mesh interact with each other, there is huge convergence issues. It's a numerical nightmare to address those. So this is a 2 megapascal line. Look what happens, because these two ties are not supported from underneath, they are not carrying any load. So the load now gets distributed differently to the ties. When this happens, right, in a railroad track, there is no cracking, right? You don't see, like a pavement, you don't see a crack or something. The track is there. Stiff stuff have changed, and then you need to also remember the track, the danger or the loss associated with the track is significantly higher than a pavement, because we are talking about loss of life immediately, like derailment and stuff like that, right? So this is basically something like this happens. It goes undetected, load distribution changes, it happens more, then there is a section that is not supported, and then you have derailment, right? So how do you track something like this? Okay, so this is where this is one of the most fun projects I have done in my entire life, and it started about I kind of focused on it 100% about 6 years ago, and it's still been going. One PhD student has completely finished his PhDs. The second one is almost about to finish on this, and I'm going to show you why. It is this simple, folks. Simply supported beam, point load. How does the shear force diagram look? This, right? What is this fall magnitude? P. So if you have any point, you measure the shear force on the left, on the right. You take the difference. What's the value? The load applied between the 2 points, right? What you can do on a railroad is you can do is you have the rail, it's a beam, right? You find the neutral axis, right? You install strain gauges, 45 degrees up, 45 degrees down. Why? Because at the neutral axis, the principal strains are oriented that way, right? And then you can actually take the difference of them. That will actually tell you the shear strain. Here also you will get the shear strain. From shear strain to shear stress, how do you do that? So tau is equal to G times gamma, shear modulus times shear strain, and shear force to tau remembers the equation. Shear force to tau V over IT, remember that, or IB, however you are taught. I think you are taught IB or something, right? So the idea is, if you are able to measure shear principal strain, calculate the shear strain, shear modulus is constant, then if you multiply, because the real properties are constant, then you know the shear force at any point. And if you 2 points, you know the shear force, you take the difference between them, what happens? You know the load. That's your load cell, right? You just install it on the train, on the rail, and then you know as the train is going, you get your wheel loads, right? Fundamental second semester mechanics of solids application, right? And then this is what this is, VQ over IT, and then this is on two sides. That's different because you're trying to take care of some out of plane bending and stuff. We're not going to go into that, but that's basically the whole concept. So we said we're going to do, I mean, this, by the way, we didn't invent this. This is there. Railroads measure wheel loads using this. It's not our invention. What we did is we actually extended it to something. We said, now let us say I am doing this exact measurement across a tie, because the tie now has a R, right? So at the tie, this difference is not going to be P, it's going to be P minus R, right? That's the difference, that's the resultant in there. And right next to it, I'll have another sensor right next to it where the load is going, that's going to give me P, right? I have P minus R, what does that give me? So without touching the substructure, you now know what load is the tie and the substructure applying, right? So that was one. There was a study back in the 1980 that actually proposed this method, but nobody actually looked into it or proved it or studied it or something until, it's actually the funny story, I was presenting my postdoc work at a conference when one of the other engineers actually stood up and challenged me, saying that I don't think this concept is valid. Why? This is theory. You see this, and he's like, theory can say anything. I don't think it's work in the field. So that basically got me started on this journey, and it's been going on for 6 years now. You know, we wrote a paper on that with some extensive modeling that caught a lot of eyes. Then we started getting funding, and we have been funded for the last 6 years to extend this into different areas and stuff like that. And we have proved a lot of things. You'll see this. So that's basically P minus R, what I'm trying to show here. So what is the research gap? Very few efforts have utilized this differential strain to measure tie reaction forces. We only proved it, we only did it in 2014, but no studies aimed at validating this measurement. So we are like, okay, how do you do this? Can you calibrate it in the field? Can you do it for tie support? Can you do it for lateral as well as vertical? Can you move on? Now we are talking about, so this is strain gauges is decades old technology. Now we have a lot of fancy sensors. So now we are extending this, and you'll see some using fiber optics to do this. We are mounting fiber optics on the rail now, and then we're doing the exact same thing. What's the advantage? Every time you have one strain gauge or one set of strain gauge, you have a data acquisition system, you have a power supply, you have everything there. So if you want to do this at 5 locations, you are putting 5 data acquisition systems, 5 power supplies and everything. Very expensive, very time taking. Fiber optics, one interrogator at the end, and then you have 2 miles of instrumentation, just one interrogator. It's expensive, yes, but you don't need track time, you don't need all the multiple, and with time the cost gets offset like crazy. So you'll see some stuff where we have done it. By the way, this is you know what this is, but the very first paper where we were trying to do, we actually started from very single, you know, almost one-dimensional elements, and then we went into cross ties and cribs, and we said when every support is similar, when you apply a P, the shear force here is minus 0.5 plus 0.5, you take a difference. Then we started changing, removing some ties, it's minus 0.866 P plus 0.134 P, again the difference is always P, right. So this was, you know, this is very theoretical for people who want to study. It will seem trivial, but to prove it in the field is a very big challenge, to make it applicable and stuff. So then after a very simple one-dimensional model, we went into a full 3D model. Okay, a full 3D model of this entire system that's calibrated using field data, and then studied that, and this is what this is. Look here what's happening. This is different cross tie modulus, 20 megapascal, 100 megapascal, 230 megapascal, different modulus. So that's supporting changing the ballast quality. With time it's becoming bad, weaker, blah blah blah. Look at the beauty here. This is the shear strains that are measured. Take one shear strain, take the other one, do a subtraction, it's always 516, 516, 516, irrespective of the distribution. And this is a full 3D model, right, saying that this principle holds. So why not make use of it in the field to actually make some sense out of what you have. So then we actually came up with, this is the 2019, this was actually in TRB, this was I think one of the first several hundred papers that were actually published and to distributed to attendees at the conference. Those of you who don't know TRB is a conference with about 14,000 attendees, and it receives about 7,000-8,000 papers every year and stuff. So it gets a lot of, and then we developed a zone of accuracy contour, and then we gave it to the industry, saying that if you are doing installations, do this, then you'll see how well it will work and stuff. So then people said, okay, the theory works, show it to us in the field. Now go and install it in the field and then see what happens. How do you go and install it in the field? You have to go, first of all, you have to calibrate the sensor. Why calibrate? Okay, again, those of you working in the lab, this is very important concept. A calibration is basically almost like a shift factor as well, right? Because if you know, let's just say, if you know 1 volt is this many strains, that's fine. You know, you can calculate everything. But the point is, when you don't have that knowledge, 1 volt is this many strains, and you only know strain, and in the field the rail property changes a little bit. The wheel is a little bit out of shape, so there is an impact load. The subgrade has changed a little bit. So you cannot just predict pure strain values or something, right? So you have to have calibration. So we did a lot of calibration. I'm going to skip some of these pictures and stuff. So this is field instrumentation, us going under FRA, the Federal Railroad Administration funding. We actually went and installed these sensors. We removed ties to artificially, this is me grinding the wheel and stuff. This is the strain gauges installed, and then this is now a plate with actual load cells that we inserted underneath the tie. We said that if our theory is right, whatever we measure with this load cell, we should be able to calculate without doing anything, just by our rail approach, just by this approach, right? So that's basically what we did. You know, there is two ways: load cell, instrumented tie plate, which is very similar. It's a tie plate with some strain gauges on it, and then we started calibrating with different type of A-frames, which is, this is how you apply loading and you study the volts and stuff. And what you see is, the first thing is, people were challenging, saying that if you change the type of calibration, your results is going to fall apart. You're going to get different results and stuff. And in this study, we did 3 different calibrations. One is where we actually, because we are working with the railroad industry and with funding from them, we were able to bring a complete railroad car, park on top of the site, use a hydraulic jack to push against it, almost like a plate load test, push against it and apply loading. No wheel, just push and a point load kind of thing. And then this is an A-frame, which actually does is it clamps the rail on 2 ends, and then there is a hydraulic jack here, so it pushes at the middle, pulls on the sides basically, because it's a self-mounted reaction frame. And when you do the calibration, look at the constants, folks: 7.8196, 8357, 8388. I think for any person with a sane mind will say that they are identical. And this, because this is field data, this is not numerical result or anything, this is real field data. When you have double decimal accuracy in the field, I think that's more than you can expect. So this is, you can prove. So again, the use of instrumentation, the use of sensors, the use of basic civil engineering principles, and how you can apply that to perform measurements in the field. So this is me again trying to mount that sensor, the plate underneath and stuff. So yeah, I mean, any day I enjoy working in the field a lot more than I enjoy working on a computer. Then we were able to say that, okay, we applied 100% load. How much of it is going by the tie reaction from the load cells, and how much of it is in the our sensor? So we are actually, we measured 42% and 37%. So what that means is it's not an exact match when you do that, our theory versus the load cell. What is the reason? Honestly, nobody knows, right? But in the field, if you are anywhere within 10% of something, it's usually good. But this is one site. The other site, when we did, we actually got exact match. This is load cell to tie circuit. This is the instrumented tie plate to tie circuit. And here you see is 55%, both of them. Here it is about 4% difference and stuff. Why? We don't know. That's what the exact data is. So this is what we were trying to show to them, saying that this is how the data compares. This is how the actual data looks. This is an animation. You'll see when a train goes, you get all these different signatures with under one pass, and then you have to analyze this data to come up with the comparisons and stuff like that. Okay, this is another stuff. Now we are saying that, okay, this is strain gauge, it's all good, all good. Now we're talking about modern sensors. Now we're talking about optical fibers. Okay, and what we can do is, let me actually switch presentations because I have more details on another one. This is our TRB presentation on the same stuff. I'm going to skip this. I'm going to skip this. This is the concept of what is known as FBG, or fiber Bragg grating. I know that in India also there are people have studied this. I don't know, I don't think on railroad application, but I know in civil engineering people have studied this. What this happens is this, folks. A grating is nothing but almost like an itch, almost like some writing. When you send light, laser, through an optical fiber, a glass basically, right? You're sending it. A light is a spectrum. It has many wavelengths. And then it goes, when it is transmitting through it, and then if there is some itching, there is going to be some wavelength that is going to interfere destructively with that itching distance. and then that wavelength is actually going to get reflected back. The remainder stuff will actually go and stuff. You can actually track what wavelength is being reflected back. And then imagine my rail extends, or my bridge extends, or my truss extends or something. Then the fiber along with it also extends. And the grating spacing changes now. So what wavelength is bouncing back is now changing. So you just track that difference, and then you know exactly what your strain is. Right? That's basically the concept. And this is an animation, as you can. Wait, I thought it was supposed to. Yeah, it's with time. Yeah. So it will actually, the Bragg wavelength actually keeps shifting when you have negative strain and positive strain. And this is what happens when you have a train. You are monitoring multiple. Now we don't have independent monitoring, folks. We have just one interrogator, and then now you are sending across the entire fiber, and multiple fibers you are monitoring, right? So now you can change, you can track how much these Braggs are changing, and then you can say this is how my strains are. Okay, so this is, so it all started with that strain gauge, that presentation, that person standing up and saying that I don't like this, can you prove it and stuff, right? That led to about 5 years of funding, but about the 4th year I got this idea. I was reading something and I said, we do this exact pretty much similar thing, but now with fiber optics. And I wrote a proposal to FRA, they liked it, and we got this funding, and then now we are working on this. We're still in the middle of this project. Next year it's going to end. So then we built a laboratory system. This is when I had come to Oklahoma State and we didn't have a lab system, so, or lab setup for railroads. So we basically set this up, a simply supported beam. This is our lab. This is, we designed this. It's a simply support. It's a roller on one side. It's a pin on the other side, because it's kind of, there is there are two rods welded on the side, so the roller cannot go. There is no horizontal deformation. And then we bought a bunch of LVDTs and a bunch of strain gauges, and we said we're going to do a conventional measurement, and then now we're going to mount it with fiber optics, and we're going to compare and see if they are going to work or not. This is the setup: LVDTs, FBGs, strain gauges, everything. This is my actuator. We're loading it from there, and then this is how the FBG system works. This is called an interrogator. This is the most expensive part, by the way. It's a very expensive piece of equipment, but the ability to monitor multiple sensors at once makes it very advantageous, right? So then what we did is, look, first we need also, I mean, again, it's kind of a, in Hindi you call it kida, right? Kind of a problem I have is I always try to study every problem numerically as well. I try to find out what's the justification. I'm never only happy with lab testing. I just don't like it. So first thing we did is we developed a finite element model for a simply supported beam. Some of you can do it in your sleep. This is nothing special, but the point is we're saying that, okay, LVDT and numerical model exact match, so we have a good model to represent our system. Now let's go and play with it. So this is just basic ground truth. Now we said we're going to install this. This is fiber optics, and this is a strain gauge. Okay, and by the way, why is it horizontal? Because the strain gauge has, it's called a dual element strain gauge. Some of it go up, some of it go down. So there's two measurements happening in the strain gauge, in plus 45 degrees and minus 45. It's in there. It's you just don't see it. It's in there. So basically this is nothing but a simulation of the plus 45 part, the fiber optics. So you mount it and then you compare, and then we were like, okay, look, this is where it is. The values are pretty close to each other and kind of around the numerical result. So yes, we are getting representative numbers on how much we can measure strain just by using fiber optics. No strain gauges anymore. And the advantage of fiber optics, folks, what you'll see is what we are doing, and you'll see this a little bit and further, we are now installing it in the axial direction. We are measuring axial strains, okay, and then we are using classical beam theory to go into curvature, to go into bending moment, go into shear force, to go into the fourth order equation where you get deflection. So now we have now kicked out LVDTs, we have now kicked out strain gauges, just fiber optics, and it's going to give you deflection and force and strain. What are the assumptions? Yes, there are classical beam theory assumptions, and we can talk about it later. So this is again some more modeling work. This is FBGs, and this is axial strains, and again we are able to match exactly the numerical model with these and stuff. So then we said, okay, can we predict rail behavior now? Now can we predict force? Can we predict deflection just by axial strain measurement and stuff? So this is the underlying theory, the curvature, double integration and stuff like that. You probably know this, most of you. Now we can do rail displacement, and look, this is my numerical model results. These are the LVDT results, and this is where my FBGs also lie. So now with just axial strain measurements, I am now measuring vertical deflection as well. So I'm measuring strain this way, and then I'm calculating deflection this way. Now you have eliminated strain gauges and LVDTs with just one sensor, right? So again, I'm going to skip these. There's a lot more details in this. I don't want to go into this. So let's go back to the previous thing as again. No. You saw this already. I'm going to skip through this. This is FBG approach. This is some coding and stuff, how this is optimized and stuff. So that's basically on the railroad side. Now let's talk a little bit about forensic investigation, and this project is going to be a great interest to a lot of you, because expansive soil is something that you all have. I mean, in India there is a big problem you have of expansive soil, and pavements do affect. So back in Idaho, there was a railroad here which had extensive, it was almost like a roller coaster ride, okay. They would come back, they would fix it, they would not do this. This is actually a sketch that my wife's sister-in-law, she's a graphic designer. She works for she used to work for Nickelodeon, you know, the cartoon company and stuff. So I told her, I said, I want something for my presentation. So she made this for me. Beware of the expansive soil monster. So this is basically, we were given a problem, and if you look at this stretch, they have reconstruction, rehabilitation, lime stabilization, impermeable geomembrane, lime stabilization again, another reconstruction, and they were having a lot of problem, lot of money. So they came and said, can you help us? Can you help us fix this? So what we did, this is the soil, by the way. Look at this this is a time-lapse video of about 5 minutes, okay. This is a PVC pipe in which the soil is there. I mean, it's packed in there. I cut it and I dipped it in water, and then just did a time-lapse video of about 5 minutes of the particle just swelling just underwater, and look how much swelling is happening just in 5 minutes underwater. It's an extreme expansive soil, right? So what they said is, can you help us fix it? So we went, we drilled a lot of boreholes, and we did a bunch of testing. By the way, my a colleague of mine who is a true expert in expansive soil, his name is Bhaskar Chitturi. He's still at Boise State. He's actually from Kakinada, Andhra. He did a lot of these pure geotech tests, and I did all the pavements and all the modeling related stuff there. and whatnot. And this is basically, if you look at it, liquid limits. Look at the liquid limits value. We're talking about almost 120 liquid limit, right? And the standard is about, if you go beyond 60, it's characterized as expansive soil. And we're talking 120, 140 and stuff like that. It's extremely expansive soil, right? And then we characterized first 10 boreholes, then we had 2 more boreholes. We did soluble sulfate content, because if there is sulfate, you cannot do calcium based stabilization. So that's one thing. But this is the most important question. There's something called active zone. I'm not going to talk to you about geotech here. What is active zone? Active zone is the depth over which the moisture is also changing and the soil is susceptible, so that you can have expansion, because expansive needs change in moisture, right? So you have to have moisture change as well. So in this site, there is about 11 feet is the active zone. What is 11 feet? About 3.5 meters, close to 4 meters, 3.5 meters, right? Can you replace 3.5 meters of soil? Can you lime stabilize 3.5 meters of soil? Can you chemically stabilize 3.5 meters of soil? You can't. So the answer is, you cannot stop this soil from expanding. That's just the truth. You have to live with it. Now, as the engineer, your question is, how do you build your pavement on top of it and still be okay, right? And this is where it's, yeah. I was attending a conference in Portland, Oregon, and then I was watching a presentation from Israel, and this guy talked about some hybrid geosynthetic system. And if you remember from day 1 or day 2 of the class here, short course, you remember my example about mattress, standing and sinking. Mattress is a very fun thing for me, because I like to analyze things like that. I actually thought, and we talked, me and my colleague thought, I said, why don't we make a cushion, so that when the soil expands, the cushion will dissipate the stresses widely, and the pavement will not heave locally anymore. It will heave over a longer distance and will not have that problem. So he's like, okay, how do we do that? I said, let's use geocells and geogrids, right? So we're going to fix that. We're going to put that aggregates in there, and rather than studying a problem from top down, now we are flipping the beam problem, where the loading is coming from the bottom and you're just dissipating it. Instead of protecting the subgrade, you are now protecting the asphalt, right? So that's what we did. We did geocells. This is the presentation I was watching. This is actually the year, I mean, I was there in Portland, I was watching, and I got this idea. I was like, man, we should do something like this. So then we proposed to them, we said, we're going to use geocells, and we're going to model again. Everything starts with the model. Is you're going to model, and you're going to study if this theory is going to work or not. So we modeled this problem, many different alignments. I'm going to skip through all of that, and then they actually constructed it based on our recommendation. Probably only 1 or 2 projects I have been involved in my entire life where they have taken recommendations and actually implemented it, right? Otherwise, researchers don't usually get this pleasure, right? So then they constructed it, and they were monitoring it. At least for the first couple of years, I was following up. There was no problems. It worked, right? So again, trying to find out problems and fixing it. Next one is, this is we're going to go through this probably quickly. Aggregate geogrid, another thing, and this is what's known as discrete element modeling. Again, these are things we did not touch of transportation geotechniques. That's why I'm showing you. This is where you're now modeling everything at a particle level, not continuum. You're actually interacting. So the geogrid is also an assembly of balls, and your aggregate is also an assembly of balls. And then you can do individual aperture stability tests and stuff, and you can check and you can calibrate the model compared to the data. And then what we did is, this is a triaxial test setup. This is a 300 millimeter diameter, 600 millimeter tall sample. Okay, this is actually from scratch constructed by me. I actually built this test device. I named it actually. I'm a big Jurassic Park fan, like dinosaurs. So I actually named it TX24, like a Tyrannosaurus Rex. It's TX stands for triaxial and 24 stands for 24-inch height. So it is still known in the research community as TX24, and I named it because of Jurassic Park. So it's called TX24. That's the first paper when we measured it and stuff. So then we I'm going to skip this. This is some FEM stuff with geogrids. I don't want to bore you guys with information like that. But bottom line is, I wanted to show some. This is an older picture of my group. It has changed now. Some people have graduated, some people have not. I'm going to show one more thing here, very related to what we have been talking about, but not something we went through. This is about compaction of open graded aggregates. I've been talking about how it is very difficult to compact, right? So we are working with, we worked with an agency called Interlocking Concrete Pavement Institute, who make permeable pavements, and they actually made us do a lot of LWD tests to develop a construction specification for them, and it was developed saying that your layer is well compacted as long as your deflection is less than 0.6 millimeters. This was our recommendation, and they implemented. But then next year they came back to us and they said, that's good, but what if the contractor does not have an LWD? They're a small contractor, they don't have an LWD. Are we going to force every contractor to buy LWD? Answer is no. But they have some standardized compactors, like plate compactors. They're like, can we develop, can we study to see if, from compaction point of view, if you, this is actually a hand-drawn sketch by me, if you take any kind of compactor and number of passes, are the slopes moving separately so that the surface deflection, the target surface deflection, is intersected at different points of time? So in other words, if I have a 8,000 pound compactor versus a 10,000 pound compactor, does that mean that because the LCM is 40, does that mean 5 passes of the 8,000 is equivalent to 4 passes of the 10,000? Is it? There is no such data, there is no such theory, and this is a lot more evidence based on empirical research, but this is very applied, saying that the contractor needs to know how to compact this, right? So this is the this was the project which you saw some videos, but then we went a little bit further. Have you all heard of what is known as intelligent compaction? So it's basically a compactor that has sensors in it. Okay, so it measures the acceleration of the layer as it compacts, and then it can detect that through check adequacy of compaction. But the problem is, intelligent compaction is very expensive and it is only available for big compactors, right? So then what I said is, these are small projects. I actually challenged a student. So we were working with a collaborator who made this thing called a smart rock. Okay, it's a little accelerometer, this is my student's hand, it's a little accelerometer, and we are saying, can we mount it on the compactor and measure acceleration as it moves on the layer? And we are going to develop a compaction index based on that. Because, by the way, those of you who don't get it yet, why can't we just use density? Because this is open graded material, there is no measurement of density, you can't measure it, it's just not possible. So you have to do something to study compaction. So I challenged my student, I said, can we do this? So him in his on his dining table, showcasing the ability of what happened? Why is it not run? That is weird. Oh, that's not good. I wanted to show this. I know this will work. I've tried this before. So we call this a smart rock, and this is him in his kitchen, and then he basically imported the data into Python with real-time measurements and stuff. And the point is, as you move the sensor, you're actually getting, from acceleration you can double integrate, and then you can actually go to displacements and stuff. So the idea is, can you do the same thing on a compactor and build something called a poor man's intelligent compaction? Because intelligent compaction is extremely expensive, right? So now we are trying to do this, and because I'm here, I'm going to show you another video. This is him and another student. There is a sensor mounted on here, okay, and he's trying to track something called an A2. That's not important, a compaction index. As the student is driving the compactor forward, we're trying to track this compaction index, and then they change direction, and you see that when it stops, there is actually a little stop in the time history, and then as he goes over multiple locations multiple times, you can actually track this compaction index and try to propose to them, after some calibration. Of course, we are not there yet, but you can propose to them saying that because there is no deflection, because there is no LWD, this setup costs $200. I mean, the accelerometer is very cheap. It's mounted on there. $200 is like what, 15,000 rupees, something like that, 16,000 rupees. It's mounted, and then can you do something with respect to just compaction, with respect to some kind of an index. Now this is empirical. This is almost like your structural coefficient stuff. We yet don't have a theory or a physics behind this. We are trying to see how acceleration changes, and the energy dissipation and the magnitude different corresponding to different Fourier frequencies and stuff, how that changes when you are compacting different layers and stuff. Skip this. Let's see, what else do I have? Yeah, so this is the project purpose, and then we started. This is what I was trying to say. There is 72 cells that constructed. So this is where pure applied research basically, and then we constructed with three different aggregate materials over with the subgrade, and then we constructed a dense graded construction platform, and for every cell we used different types of compactors to compact and then measure the response and stuff like that. So this is a company called Weber MT. They actually lent us the compactors for free, so we didn't have to pay for it. And then you'll see this is the location. This is behind my lab. This is what the cell location was. This is aggregate procurement. What's going on? The aggregates, or sieving the material to say establishing target gradations. This is construction, you know, you start from the grading and everything, then you do DCPs to see average CBRs. Today in the tutorial I'll show some of this data to you to see how the average CBR is calculated and stuff like that. And then this is the DCP testing happening. At night we're testing, and then we were able to do LWD testing. This is the construction with the target, you know, laser to see how tall it should be. Then this is, because this is such small test sections with so much variability, we actually constructed a little formwork. So we would actually place this, then pour the aggregate in here, and that's one section, and then move the formwork to another location. This is what was happening. There's a video showing that. This is a drone video. I think I've shown you this. This is LWD stuff. How surface deflection. The green layer basically shows that for the compaction platform we were able to get uniform compaction throughout and stuff. And then these are the different compactors. This is me pouring diesel into one of the compactors. This is us compacting. Everybody was trying to compact, multiple of them working together. Then after every compaction we did LWD testing and stuff like that to see how testing is done. I'm not going to go into data analysis here. And then smart rock, you already saw that. This is what it is. So anyway, the objective of this first part today, it's almost done for that. We were trying to study, like look at different challenges you can see, and some of the topics we haven't touched about instrumentation, how they are used, what they can tell you, and how we can integrate that and stuff like that. Okay, all right, let's break for now. We'll take a 15-minute break. Okay, folks, as of now, I have covered pretty much everything that I thought of covering in this 5 days. Okay, we have another, close to 90 minutes to go. Uh, and I have the geo track to show you. I'll show that to you. It's not, uh, that's not a 90-minute thing. I can always try to find some other stuff, but I would rather have discussions or anything that you guys are, anybody is working on research that you are struggling with, or you want to discuss as a community here. We can just brainstorm together or something. So any volunteers, anybody who is doing something, there is a reason you all came to this class, except for Sahu sir asking you to join or something. I mean, that may be some reason for some people, right? Some of you I can see smiling. I think that was the reason. That's okay. But I'm sure there is other reasons as well, right? So anybody wants to volunteer? Any questions that you want to discuss? Any challenges? Go ahead. Okay, that's a very good question. So railroad design does not really have like a design life like that. So because if you think about it, it's not really a fatigue based design or anything. It's a material decomposition based design, and you don't really have exact uh, design life per se. What they do is they try to limit the stress levels at different to different values. That is how the design is done. A lot of it is actually based on very old methods. Uh, and after that, one unique thing about railroads, at least in North America and Europe, is the inspection is very regular, extremely regular. I mean, you'll be surprised by the technology that gets used to regularly track it. And that is the reason, is because the stakes are very high. The moment you have a derailment, you're talking millions and millions of dollars and people dying and all of that and stuff. So it gets uh, evaluated, and then depending on the track location, they can have what is known as, so the ballast, it can have different things. So ballast undergoes what is known as fouling. I told you, right? Fouling is dirty basically, and degradation is one of the primary mechanisms. Like when ballast churns against each other, it gets fouled and stuff. So they have something called edge cleaning, shoulder cleaning, where what happens is, uh, the way railroad tracks work is, and it's a very interesting problem as well. So if anybody wants to go into some really deep analysis and stuff, this is kind of how a typical railroad track looks. I mean, the track lies here, right? So the rails are going that way and stuff, right? So when it rains, and this is all ballast and stuff, so they have a shoulder, they have certain specifications how to do shoulders. I'm sure Indian specifications have that as well. The problem is when you have your cross ties here, this is a tie, let's just say, right? And then you have ballast all over here, and then it rains, or it starts getting fouled. So there is a lot of areas here that are fouled. Then it rains, right? The water actually washes the fines towards the shoulders, right? So it actually gets here and here. So with time, you'll see the ditch or the shoulder area getting really dirty and everything, and that actually prevents free flowing. So what they do is they come and they do what is known as shoulder cleaning. They actually have an excavator kind of thing. They actually dig like a trench. They pick up the material, they run it through a sieve shaker, reject all fines, and the big material they put it back and stuff. And depending on the site, that can happen once a year, once in 6 months, once in 3 months, once in 4 months and stuff. I mean, it all depends on how bad a site is, right? And resurfacing, like when they have a deformation, like they have the track profile going out of geometry and stuff. In busy corridors in America, like the Northeast corridor where it's very passenger heavy and stuff, they actually do the inspection every 2 weeks. Every 15 days they have a detailed inspection, and if there is a problem, they come back and fix it. So the site I was showing that we were working, they actually had to come back and fix it every month once, and that is why we fixed it, and it was able to be pushed to at least once in 2 years and once in 2.5 years and stuff, which ended up being really nice. So there is not real design life per se, but it's site dependent. It's not unheard of for them to come and address something every month if it's a very critical site and it's having a lot of problems and stuff. No, I mean they are, yes, but 95% to 96% of the ties are still of wood or timber ties. If you take the total track mileage in US, about 5% or 6% are concrete. Rest are timber still. Timber has certain advantages. There is an abundance of wood, and it also has some advantages because it's more absorbing. It's not as rigid. It doesn't degrade the ballast very bad. But when you go to higher speed, higher demand, like Northeast Corridor, which is where Amtrak runs a lot of the passenger, there is a lot of concrete ties, concrete truss ties, but a lot of timber as well. Anybody else? Yes, Atanu. Okay. Binder. Uh-huh. I'm not an expert in anything. I'm just somebody who works. I don't call myself an expert in anything except movies. I know a lot about movies. If you want to talk about movies, we can talk. Go ahead. So modulus. So all I can say is I have done FWD work on cold in place recycling, cold mixes and stuff, and some modeling, some FWD and stuff. I have not tested them for resilient modulus, but the modulus we used was 100,000 psi. If you want just one E value, so it's about 100. So a typical good quality aggregate was about 40. As I showed, 40, 45 is a very good quality aggregate. We used about 100, 80 to 100. That's all I can say. I've not tested it in myself, but that's the FWD and the run triaxial testing, fit a K theta model, see if what do you mean by triaxial? Like resilient modulus or okay? And it is pressure dependent. Then it is pressure dependent. I mean, it is what data says, right? I mean, it is yeah. I mean, you can. Are you able to run a shear strength test? Can you apply confining pressure and shear it? Is your device strong enough to shear that material, or is it too strong? Right. I mean, if you do you have seen resilient modulus, but if you do like a triaxial and you actually are able to plot a more Coulomb like this, then it answers everything. Then it's a frictional material for sure. Try that. Try try 3 different confining pressure, at least 2 different confining pressure. Do you see a difference in shear strength? That will work. Anybody else? Come on guys, we have to talk till 1 o'clock. Otherwise Sahu sir will not give me lunch today. Okay, we can take a look at GeoTrack if you want. So I think I should do this. Okay, so oh, what? So this is the original paper for GeoTrack. I will share it with you all. It's again a layered elastic program. It was developed by Professor Ernie Seelig, who is no more, but he was a professor at University of Massachusetts, and the whole idea of GeoTrack is that it is a beam that is districtly supported by the ties basically, and it's a BOEF, beam on elastic foundation model basically, but the way the loads are transmitted is that you take the loads Q1, Q2, these are the 2 wheels on the two rails, and then you are dividing the tie into 10 little circles. Okay, the tie ballast or the sleeper ballast interface is divided into 10 different circles, and those circles is where the pressure is applied. And if you look at one circle, it's nothing but a tire applying a load on a pavement, right? So beyond that, it just becomes a problem of superposition and stuff, right? So then you have, it's a 11 tie section where they actually model the force going into the track and stuff, and that's basically the shape, 3-dimensional multi-layer model, elastic response, components are shown. Rails are represented by linear elastic beams supported by a number of concentrated reactions, 1 at each intersection. The rail spans 11 ties and are free to rotate, and then the connection between rail and tie is represented by a linear spring, which is given some constant. Ties are represented as linear elastic beams specified by modulus of elasticity, and then the ties are supported by the underlying layer. And this is some some mathematics underneath there. Again, go back to your beam theory and stuff. This is some of my hand notes and stuff, and it can actually do some hysteresis behavior, some stress dependent behavior and stuff like that. So back in 2015 or 2014, when I started as a faculty at Boise State, we talked to this Association of American Railroads. They had very interesting problem. They had an executable version, like a DOS executable version of GeoTrack for which they didn't have a source code, and they had a source code which would not compile, so they did not know which one was it for. So it was not for the executable version. So they basically gave me and said that, okay, figure this out, check this code if it is correct or not, recompile this, fix this and stuff. So that was my first master student who did all of this work, and we developed this GeoTrack code that I'm going to show you right now. And we can show you what I think. Sahu sir is not here right now, but I think there is a good need for something like this for India, and you all people who are pursuing research and stuff, you should think about it, because beam on elastic foundation is something that pavement community has really been an expert in. So just do something with it. So what my student did is, she was again a champion programmer, and what she did is she made this into a GUI completely. So this is the GeoTrack GUI. I'm going to launch it, and as I said, I cannot share this with you. I would love to, but I am not allowed to, because this is a private company. They sponsored this, so it's their IP. They have in fact told me if I give it publicly, I may face lawsuits and stuff. So of course I'm not going to do that. So what you can do is you can either input material properties manually, or we'll do something that's much easier. I'm just going to go, no, this is an input file, and we're going to take a look at this together and see what's going on. So this is a layer. There is 5 layers. The modulus is 40,000, 20,000, 4988, 4350, and whatnot. The modulus, the Poisson's ratio values, how deep are they, what is the unit weight, what is the K naught value, and what is K1, K2, K3. These are stress dependent parameters. Then you go to rail properties. You can actually define rail properties, like these are some predefined rail sections with defined properties. And folks who are doing masters, if you want to do a thesis and stuff, remember this was done by a master student for her thesis. This is not PhD work. This is a master student developed the entire code from scratch. She had no clue what railroad was, and then she started, and in 2 years, less than 2 years, she did this. Then tie, there is other, there is concrete, there is wood, you have different things. And then load, how many axles are you applying? This is 3 axles basically, because that actually usually represents the stretch. Then it says first tie, where it is located, last tie, first segment, last segment. That's basically some parameters in terms of where load should be applied. So then you can actually just do run analysis, and it's just going to go. I'm going to just save it as GIAN. Save. Oh my God, what the heck just happened? I just ran it right now. File open. Okay, good. Thank God. I think I did something previously wrong. So what it does, folks, is it plots by default some plots, which basically is tie number versus rail and tie deflection. So where the load is and how the ties are deflecting, and because of the location of the loads. Tie number versus tie bending moment. So now you can track the bending moment of individual ties, because that's actually a failure criteria. Tie number versus rail bending moment, and then rail seat reaction. This is what I showed you about the strain gauges and stuff, like how much force is being transmitted and stuff like that, right? But not only that, what you can do is we developed this open-ended plotting window where you basically say what tie are you interested in. Okay, I'm interested in tie number 1. What segment? Remember, every tie has 10 segments, and we divide it into 5 because it's axisymmetric, like half of it, and then you select all the segment and what kind of plots. This is vertical displacement. So now it is plotting the segment numbers where each the segment is. Segment number 1 is under the rail, so of course that has the highest deformation. As we go away, it's in the middle of the track and stuff. So that's how it is doing less and stuff. And then you can change this to bulk stress, where the bulk stresses are high, of course under segment number 1 because it's under the rail. Imagine how a load is transmitted, right? If you think about it, this is actually a very interesting problem in railroads as well. If you look at the cross section, this is the rail, and there is a tie underneath here, right? So the loads are coming through this and then going like that and like that. So the question is, when you design a tie, do you really need the same thickness in the middle? You don't, right? Because there is nothing happening here. So that's the reason tie designs are usually like this. I ran out of space. That's how ties are designed basically, because the middle thickness, you don't need it. It's thinner. There is no load transmission happening. It's beam, right? Save material and stuff like that. So that's what's happening here. The bulk stresses are also higher because segment number 1 is actually here. So it's actually somewhere. Yeah. And then you divide that into segments going into, and 5 is kind of in the middle and stuff like that. So that's bulk stress. You can do maximum principal stresses, you can do minimum principal stresses, and all of that. So this is just running the layered elastic analysis, and you can give all the output and everything to run this. It's nothing rocket science, but it's very useful tool to do that. So this is what we developed for them. We gave it to them, and they didn't. Original plan was for us to develop an official GUI for them, but then they got into because they are a company, they have software design standards, like this is how software should be, and I'm not an IT person, so we just handed it over to them. And then you can do a lot of other things. You can actually do something like query track response. It's saying that, okay, what do you want? So I'm going to say, what happens on tie number 1 at a depth of 12 inches, less length from first into tie number 1 at a depth of, let's just say 6 inches from the set, and then you just query. It actually gives you the stresses and strains, like what is the vertical deformation, what is the bulk stress, what is the vertical principal stress, and everything. So just like GeoTrack did yesterday, right? You could do IIPAVE did yesterday with the query points and stuff. You're doing the exact same thing here. That's one aspect. The other aspect you have is you can do permanent deformation calculation. So basically what you can do is QU just based on the SSR stuff, unconfined compressive strength versus vertical stress. You can actually mention a QU, Q50 or something, and then calculate. It will actually give you sigma D. It will actually give you permanent deformation is 0 here. I don't know what happened. 20. It's been a long time since I played with this. So this was, it's not a number, maybe because it's the classifications. probably too small. I don't know. I don't remember exactly what the deal is, but there is. Oh, sorry. I'm so sorry, guys. Yes. In minus infinity plus infinity. Wow. 1000 load reputations. QU. I don't know why it's doing that. Okay, I'm not going to waste time. The other thing you can do here is run dynamic analysis, which is basically in GeoTrack or not in GeoTrack. In the original GeoTrack, this was not there. In ARIMA, what they do is they say that static. This is all quasi-static, right? Static analysis. They say that a rail, based on its diameter and based on the speed, applies certain amount of dynamic loading for this. There is a fixed formula. It's not something you're not doing true dynamics or anything. There's a fixed formula to translate that, so you can actually do that. Wheel diameter, if you just say I don't know, 24 inches, and vertical speed is 45 miles per hour. If you do run dynamic analysis, then it actually can plot you figures or anything for the dynamic case. Now it enhances the load that you are applying. It just multiplies that by a factor and then does that. Okay, and what is this used for? I'm going to show you something very quickly, and that's pretty much going to be all I'm going to do today. Give me one. Oh no, not here, sorry. This is the importance why you do this. I'm going to show this to you quickly. This is another ongoing project. So the whole idea is why you need this is because track conditions are non-uniform, superstructure and substructure get degraded, and performance is influenced by the degradation of superstructure, substructure, and we need to frequently monitor that. And one of the factors that you monitor this is something called track modulus. Okay, in pavements you did not hear something called pavement modulus. You heard about individual layer modulus. Here also that exists, individual layer modulus, but you also represent something called track modulus, the overall load deformation behavior of the entire track, and I'll show you the equation for that. And modulus is an indicator of the quality of the track. And in the US, I mean, this is a project I currently have with the Department of Defense or the Army Corps of Engineers, because they have certain maintenance standards. They say that if you have 5 ties that are bad consecutively, then that track is bad. That's just an empirical, previously experience wise and stuff. So they actually contacted us saying that, what is the meaning of these 5 ties? Is 5 ties actually bad, or can it be made 7, or should it be made 3, right? What is the impact of all of these on track modulus? How does the stress strain dissipate or load distribution happens and stuff like that? So that's basically our project. So our questions is, what is the effect of support conditions underneath a tie on track's load deflection behavior? What is the effect of a weak zone under certain ties? What is the variation in properties of weak zone? And how sensitive is track modulus to variations in different substructure properties? So if you have a track with certain modulus, now your subgrade changes. Is that having a big effect on the modulus? Or ballast change, does it have a big effect on the modulus? Because that's how it's indicating the overall structural health of the track. So in this one, what we have done is the theory behind track modulus, how does it represent track conditions, what factors influence track modulus, what are the traditional measurement approaches, what parametric numerical studies have been conducted, what are the measurement systems, and stuff like that. So this is the theory. Okay, this is theory. If you look at it, track stiffness, very first class I told you this, stiffness versus modulus, and somebody actually, I think yesterday or day before during the lunch, was asking me about the significance of stiffness and modulus and stuff. This is where it comes into picture as well, right? Stiffness is P over delta. Modulus in this case is actually Q over delta. Q is basically, if you study like a beam on elastic foundation kind of thing, which is where a uniform pressure, a linear load kind of is applied, if you take that Q is basically U times delta, so U is equal to Q over delta. So Q technically, or sorry, U technically is not something you can calculate just by one measurement or something. You have to have like a bowl or something. You are not, it's not a point measurement. Deflection is easy. This is a spring constant, right? You just stand something, it deflects P over K or P over delta. It's very easy. Modulus is an output of your analysis of your bowl or multiple measurements, right? So what are the influence factors? There is flexural rigidity of the rail, because now you are not directly applying load on a multi-layered elastic system. You actually have a steel. That beam is supported by some discrete supports. That beam is on an elastic foundation. First beam is the rail, second beam is the cross tie. Underneath that is your pavement, right? So your analysis changes a little bit in this case, right? So that's the flexural rigidity does affect quite a bit. Moment of inertia, cross section. For the ties, it's tie materials, concrete, wood. What is the stiffness? What is the E value? What is the I value? Because now we're talking about bending, right? EI, bending stiffness. You calculated that quite a bit in structural analysis and stuff. So that's EI. Tie spacing, depending on how far the ties are, the interaction between the rail and the tie is going to change, because the tie, very closely spaced tie, means the whole system is very stiff, right? So tie spacing, missing tie, which is basically another way to represent tie spacing. Tie condition, if the conditions are bad, if they are degraded, they are not as good in bending, stiffness and stuff. Is there any water in this thing? Yeah, that's one. That's tie condition. Then you have a hanging tie. I told you this about already. If there is contact is missing, right? Fastener stiffness, again the fastener is between the rail and the tie, that stiffness affects as well. Sublayers, subgrade layer, subgrade condition, thickness, moisture condition, ballast and subballast, ballast condition, compaction, fouling, degradation, ballast depth and everything. So all of this is going to affect your track modulus, right? This is some empirical, again, from some past work that Professor Seelig and others have done, and what they did is, if U or track modulus is less than 14 megapascal, then it's a poor track. Between 14 to 28 megapascal, it's okay. Greater than 28, it's good. So the idea is, let's just say, first of all, how does this correlate with actual response that you see in the field, right? That plus how is this affected by, now I am changing my ballast, now it's a clean ballast to a fouled ballast, dry subgrade to a wet subgrade, type 1 subgrades, high plasticity clay to a low plasticity silt, all of that thing, how do they change, right? That's what this is. So how does track modulus affect? This is actually a very very interesting plot. I want you to pay attention to this. X axis is deflection, y axis is load. Okay, imagine resistance. I'm talking about the resisting load, not the applied load, like the load due to the system supporting. When there is a train, at the very beginning, if there is a contact, loss of contact, like a hanging tie or something, then the track will go down, but there is no resisting force. So you will have a deflection that is kind of flat. Only deflection increasing, but load is not increasing, and then it will pick up. That's what this is. Flat, and then it picks up. So this flat is the void. So if you can measure in the field the deformation of the track as a train goes or something, and then you plot the load deformation curve, you can actually calculate the voids if there is anything at the interface. And then, so if somebody assumes a linear behavior and draw a line parallel to this K, this actually, it's almost like, elastic modulus versus resilient modulus. Remember, elastic modulus happens at zero strain, but in the actual track with voids, the modulus, the mobilized modulus or stiffness actually comes after some deformation, right? So this is how the mechanics works for tracks. Okay, so how can you measure? How can you measure track modulus? We talked about resilient modulus, we talked about FWD. Now similar measurements, but in the railroad track. How do you track modulus overall, right? What you can do is, this is pure theoretical approach. Talbot, you've heard of Talbot. Talbot is the mechanics person, very, very famous, developed a lot of conceptual, theoretical, applied mechanics concept and stuff. You have multiple loads on the track, on the rail, and then you measure deflections at each point. Because U is kind of an area, if you integrate from minus infinity to infinity, it's kind of an area, right? It's a summation, many summations, it's basically area. And then you summation of P divided by summation of W, that kind of gives you an idea of your track modulus, right? How do you measure this? This is theory. How do you measure this? It's very, very difficult. Like you have one location of loading. How do you measure multiple deflections like that, right? You have to have many sensors, or do like a imaging based work and stuff, like DIC, digital image correlation and stuff, where you do video based measurements. Then comes another approach. This is called deflection based or reduced area. What they do is they first load it with light car, like unloaded, what do you guys call it, bogie, right? The language is very different, by the way. Bogie is not a dabba in America. Bogie is basically a set of axles. So like what we say is train ka bogie, it's very different. But like a rail car, that's what a car is. A bogie, a dabba is basically a rail car. So if you take a rail car, a lightly car, like not loaded or maybe half full, and you load it, and then you have like a deflection pattern, and then you fill it completely and measure another deflection pattern. The change and the summation of PH minus PL, which is basically the difference in the load, heavy minus light, and divided by the summation of the area or the difference or the deflection changes, that actually gives you an idea of the modulus. So this is another measurement approach. How can you measure? Like, in pavements it was easy, FWD, right? You just measure. Here you have to, there are many different options and different challenges. This is the mechanics based approach. This is what your software can give. Like GeoTrack, when you run the calculation, it will give you a track modulus, because it does deflection analysis and everything, it can take an area, it can just calculate. It's pretty straightforward in there. So that's what this is. QS is equal to U times W, and then U, this is your beam equation, and then you solve it, and then you actually can calculate U is equal to third cubic root of K4 divided by 64 EI. So, and then track stiffness is P over W, which is at x equal to 0 and stuff. So that's the mechanics based approach. But it does not identify non-linearity. It is only a linear based, like P is equal to K times delta kind of an approach. It doesn't do at beginning, it's soft, soft, soft. As you load more, it becomes harder, harder, harder. The stress hardening behavior doesn't get captured. So there is a need for all of that as well. Tie on elastic foundation, it's pretty similar stuff, where you can just study the tie on with Winkler's theory and stuff. So this is GeoTrack. I already showed you the concept of it. It can actually measure or give you a modulus. Rayleigh ties are linear elastic beams. Elastic stress dependent behavior can be modeled. Effect of only vertical component of wheel load. You don't have the ability to have horizontal. That's the big one. How does a rail go, folks? If you have a curve and a rail rides on it, who knows this at least? If this is a track, where is the wheel flange? Is it on the outside? Everybody knows that, right? That's good. So it does inside. So there is an inside here and there is an inside here and stuff like that. So when you travel, it actually pushes against this quite lot and stuff. So there is a huge lateral component on railroad tracks. It's very dissimilar to pavements and stuff. You have some shear. This actually is very big, and the way you characterize it, something called L over V ratio, lateral load versus vertical load ratio. And L over V is a big indicator of derailment potential. If you have really big L over V, that's bad for your track. Okay, so these geotracks and stuff, they don't have that. And loads, we are only looking at the tie locations up to 17 ties, and it's unable to simulate local variations in traction, just like any multi-layer elastic theory, right? We said in your IIT PAVE, your LSIM or your BISAR or something, you cannot measure or you cannot simulate variation within a layer. It's one property, it's one E value. So that's similar to what GeoTrack does, but you can do that using something like a numerical model like Abacus. This is the model. I showed you some pictures of it. So this is what we are doing and stuff. Let's take a look at this. This is pretty interesting stuff with track modulus. What changes? Concrete versus wood. Concrete is stiffer, ties, talking timber ties like slippers. Concrete is stiffer, so that's higher modulus. Wood is lower modulus. Tie spacing, 18 inches versus 30 inches. Tie spacing, when you have closer ties, the bending stiffness increases significantly, right? It's a much better supported. So that's the reason it's higher. Fastener stiffness, look, 350 or versus 26. This is in the US units, and or kilonewton per millimeter is here. So the point is, if you increase the fastener stiffness significantly, this is different vendors providing different values and stuff. So if you change it, your track modulus does change quite a bit. Ballast in megapascals, so 20,000 psi versus 80,000 psi or 138 megapascal to 551 megapascal. Subgrade modulus, 10 KSI to 40 KSI, subgrade, subballast. This is subgrade. Look, subgrade has a huge component because there is a lot of variation that happens. It has a big effect on track modulus. Similarly, subgrade thickness. Like now you will ask, what is subgrade thickness? Because subgrade is semi-infinite, it's an analysis, right? But at what point you are hitting bedrock? Because bedrock is going to support pretty good, right? Beam on elastic foundation. This is, you know this already. We're trying to, what we are trying to do is trying to study this. We're trying to, this is an FEM, and we have 1 tie, 2 ties, 3 ties, 4 ties, 5 ties. We're actually simulating gradually the weak zone, increasing, because we can't do that in something like GeoTrack right now. That weak zone is not possible. So that's studying the effect of modulus and stuff like that. That's pretty much it. On this side, I guess, let me see. Let me take a look at the program and then we'll see if I didn't cover anything. But I don't want to be unfair. This is the proposal. So let's see, what did we cover? Days kind of got mixed, but let's take a look at it. So pavement and railroad track design, philosophy, historical development, we did it. Substructure layer, their importance, mechanistic empirical framework, statistically based soil exploration, you guys did all of that. Introduction to subgrade evaluation, laboratory and field methods of subgrade evaluation, CBR, DCP, laboratory and field methods of subgrade evaluation, FWD, LWD, GeoGauge. We introduced everything. We didn't go into details of LWD. Maybe in the tutorial we can take a look. Interpretation of DCP, that's what today is. We did FWD already. Oh, by the way, did you guys collect FWD data yesterday? In the FWD demo you had one, right? Did you collect data? We did? What? Okay. Oh, old data. Well, we have played with it, so I don't want to. I was, if you had collected yesterday, I would have tried to do something. Mechanical properties, shear strength, modulus, we did that, permanent deformation, shear strength characterization, Mohr circle, failure envelope, drained versus undrained, analysis of subgrade and aggregates, shear strength data, you already did that. You did the Mohr circles and stuff. Repeated load behavior, resilient modulus, permanent deformation, resilient modulus data, you did that. Consideration of stress dependent, ILIPAVE, you have done it. Anisotropic behavior, we did it. Introduction to lab and GeoTrack, we did it. Right? I think we've pretty much finished everything. At least that's what I have planned. On the tutorial today, I'm still going to show you the last thing, DCP. What I'm going to do now is basically turn it over to you all, and what I want you to do is this. Go to your Menti. Is it working or saying I have not launched or something? Working? Okay, all right. So this is a feedback form that I have for all of you. Take your time, please. If you want, you can join on your computer so that you can type. In fact, I would suggest do that. Why don't you join on your computers? Because there is a way to join with a code. I can give you the code so that you can type. Or is everybody comfortable typing on cell phones? You're okay. You guys are young generation. You text all your life, right? You probably ask your parents for dinner by text. And please give detailed, honest feedback, because this is very important. We spent a greater part of 5 days together. I want to know what you liked, what you didn't like. लाइव बंद कर दो